Just to pass the slides, you can just do this to pass the slides. And then we can use that. Okay, so guys, whenever you are ready, you can start.
Hello everyone, I'm Eric and here's Thierry, and I'm going to talk about our project. Firstly is our background. The structure of bridge made of nature or artificial materials that across physical obstacles like mountains, rivers, and more. And they were first popular in Mesopotamia, and since then the bridge has to have begun to develop slowly. And first, the structure of bridge is very simple. Just use the materials from nature, like wood, stone, and so on. Then, ancient Roman used build bridge used like some stone or sand, lime, and other materials. And the Indians used to build bridge used bamboo on chains. And then in 1779, the Iron Bridge was completed in the UK, and it was an engineering miracle at the time because it was the first iron in the UK, in the world. And then, so far, the development of bridge has become more and more mature, and various types have appeared, and the types become more and more, such as beam bridges, trans bridges, suspension bridges, archers, and so on. I want to focus on suspension bridges and the beam bridges. This picture is types of beam bridges. At first, the original design of the beam bridge is very simple, and just like a warden across the river, and then people use lime, cement, and to build stronger, longer beam bridges. And an example of the world famous beam bridge is Pontchartrain Lake Embankment in southern Louisiana, and which used high-strength reinforced concrete to make a large number of the parts. And this picture is about suspension bridge type. And suspension bridge type has a fixed tower bridge, and that connect by the suspension cables, and the suspension cables fixed on the end of the on the bridge, then carry most weight of the bridge. And the famous example is the Golden Gate Bridge in San Francisco. This kind of bridge can meet a long distance crossing, so we always choose this design of this suspension bridge in some bridge construction. And the next is our experimental procedure. And firstly, we use scissors to cut 4 straws of same length, and we use scissors to cut out 2 straws of 3 centimeters long, and then we apply 2 long straws to each side of the short straws, and with tip, and then tip them on the table. And we do 2 same models as a bridge tower, and then we stick both on the side of the table with about 13 centimeters to place another straw. Then we insert another straw in the middle of the bridge tower, and as a bridge deck. And then we unfold a large paper clip, and then fold it into a V shape, and then poke the paper clip to the plastic cup, and then as a roller tester. and then use a small clip to connect to the bridge deck, and as a loader tester. Then we add coins into the cup, and then until the bridge collapses. And then we use the electric scales to weigh the weight of the coils, and then we record the results on the book. And then we repeat the experimental steps at least 2 times. Then we this is the beam bridge. Then we replace the beam bridge to the suspension bridge. And the suspension bridge, we cut a 2 meter long line, and the one end of the line is fixed on the table, and the other end of the line above the first tower bridge, and then wrap twice on the surface and fix. Then after another tower bridge, and then fix on the table. Then we repeat the previous method like last one, and we use the coin and record the result on the book, and then compare it.
Okay, I'm Turing. Then let me analyze the data and the conclusion. After the experiment, we counted the data and we put it on the table. We can find that the data is floating, so we need to get the average to be as the experiment result. So the average value of beam bridge is 328.7 gram, and the average value of suspension bridge is 457.7 gram. So we can get a conclusion that the suspension bridge has stronger load capacity than the beam bridge, and we need to know why. Then we try to do some physical analysis. The first picture is the principle of the decomposition of force, and the formula for calculating the force of the decomposition. It's the original force F1, and we can split it into 2 forces, F1y and F1x, and this is the angle theta. So we can use these 2 formula to get the accurate force. We can get the force number of these 2 forces. And we need to apply this principle to suspension bridge. I made a picture to show you that at first the bridge surface is subjected. It will carry weight, carry gravity, and it will cause the bridge deck sink. And this is thread, or we can call it cables. It is connected with the bridge deck and the bridge tower. Then it will generate or create a tension force. So the thread will transfer a part of downforce or a part of weight to the bridge tower. So that's why the suspension bridge can load more weight than the beam bridge. And as an interesting phenomenon we found during our experiment is, after we do the experiment of suspension bridge, we can find this tip we use to attach the bridge at the bottom of bridge tower and the corner of table. It seems like there you can see there is a gap. It become loose and it become more flexible. It shows that the bridge tower indeed carry more weight than the beam bridge, so it will happen. Conclusion ideas for future research. because bridge technology is more and more advanced now. It's unlike the past. People can build a lot of like cross sea bridge all over the world. So human hope that the bridge can be built in various environment or the more tough topography, but the bridge will face more challenging and the tests. The analysis of force we discussed before, it was in the two-dimensional, we call it 2D. Like that is our force analysis picture, and we can put it on the x-axis and y-axis. But in the real world, we are in a three-dimensional world, so we need to consider more like there's another axis, z-axis. We need to consider about it. So the force will come from a lot of different directions, and the bridge will receive force from different angles. We can see from the x-axis and the y-axis, even the z-axis. So as the force, so as which we can say that the wind can do that. Wind can give the bridge the force from another angle, and also the wind can make the bridge to flutter. So the flutter is really a little bit more complicated to explain, and maybe we don't have enough time. So I write some definition in the handout. You can see that. And we prepare another video to show how the flutter will affect the bridge. It's the bridge and the wind below from one side to another side, and the bridge deck will shake, and it will shaking more and more. We need to know the wind is a constant speed wind, so the wind speed cannot change, but the shaking of bridge deck will shaking more and more, and finally the bridge deck will broken. So it's a really serious problem we need to consider in the future. And how to solve this problem? There is only this one example. I hope to introduce it to everyone. The Xichaomen Bridge is China's largest suspension bridge, and it's the second largest suspension bridge in the world. It was designed to have a navigation level about 30,000 tons, and it can have service life 100 years. So how to do that? It uses a technology called the split type steel box stiffening beam to build this bridge. We can see all the materials. It's not a whole bridge. All the materials is split. So so each materials will not have their frequency is not same. So when the wind have a fluid effort to the bridge, the different frequency of the materials will offset this power, this force. So so the bridge meets the requirements of wind stability, and the critical wind speed of the flutter reach about 88 meters per second, so the bridge can resist the 17 plus super typhoon. And this is our reference, and this is all the content of our speech. Thank you for listening.
Thank you very much.
Thank you.
I would have just a very quick question, actually, because you mentioned something very interesting about the wind
Yes.
and the bridges and how that is a danger. So I know it's the extension, so I'm just going to ask you the question.
Yeah.
So you know how every object has a natural vibration frequency.
Yes.
So what happens when the wind is exactly at the same frequency as the natural frequency of the bridge? How is that called? Do you know? Because obviously you've sort of looked into it. what will happen if the frequency of the bridge
Yes.
reaches the natural frequency of frequency of the wind reaches the natural frequency of the bridge? What will happen in that case?
Yeah, it's like I think it's a little bit like our mini project. We
Yeah.
use the frequency, we use isolation.
Yeah.
So if we got the same frequency, the power will 10 times or much bigger times than its original one. So if the natural frequency is same, fortunately it's same to the bridge frequency, the shaking, like the video, will be bigger, shaking more, and at last it will the bridge deck will get a lot of force. Finally, it will break.
It will break. Yeah.
Yeah.
So that's called resonance. Resonance is when you've got the same frequency of the
Yes.
wind and the natural frequency of the bridge, and that actually happened. I think it was in America, a very famous bridge started really oscillating
Yeah.
and then broke. Yeah. So very good. It's really good that you looked into that. Any other questions?
Yeah.
Daisy? No. Right. Okay. Right. Thank you very much, guys. Right.
Thank you.
Well done.